All right, I'd like to introduce the last speaker for the hardware session. This is Professor Naveen Verma, who has a PhD from MIT and has been a professor at Princeton since 2009.
All right, thank you very much. Let's see, first of all, it's a real pleasure to be here. In fact, I think one of the really compelling things about this whole meeting is that we've got people in the room who are kind of at the circuit level, kind of at the architecture level, up to the algorithms and the framework. So I think it's a real opportunity for all of us. So it's a pleasure to be here. Let's see. I'm going to talk about this thing in-memory computing for a little bit. It's something you've probably heard about. Let me just put it into a little bit of context before I start rolling. You've seen already that hardware acceleration has been really critical. It's allowed us to really reduce the energy, increase the throughput, so that we can run these kinds of applications we care so much about on these very resource-constrained devices. But in fact, it turns out that for some of the kernels that are really critical in machine learning algorithms, in particular high dimensionality matrix vector multiplication, it turns out that the gains you can get from traditional digital acceleration are restricted or limited. And the reason for that is that we're dealing with these computations with these high dimensionality data structures. And so as a result of that, we end up having a lot of costs associated with memory accessing and data movement. And for that reason, sort of traditional digital acceleration actually faces some constraints or restrictions. And that's where in-memory computing comes in. In fact, this thing that I just described to you, this limitation I just described to you, can more generally be referred to as the memory wall. The memory wall is something that's often associated with accessing off-chip memory. In fact, it's much more fundamental than that. This occurs anytime you've got data storage separated from where you're doing computation. And in particular, the problem that arises is that the way that we store data is in these physical things called bit cells. Those physical things have some area. And so if you have a lot of data that you need to do for some computation, this now requires a corresponding array. And so now you have a communication cost associated with taking data from the point of storage to the point of compute. And that communication cost is, in fact, potentially very severe. It's a communication cost that increases with the amount of data that's involved in the computation, the size of the array, as you can see here. And so if you start to look at sort of practical numbers here, what you start to see is that as we go to sort of even modest-sized arrays up to these larger arrays, this energy cost, as one metric that we might care about here, can very quickly dominate over the cost of actual computation. And of course, you can see here that I'm pushing to lower and lower precision, which is a trend that we find in some of the deep learning systems, for example, that we're interested in. And so this cost is fundamental. The question now is, what do we do about it? And so let me sort of think this through here. The fact that it is fundamental means it's not going to go away. So what we can do is amortize that cost. And in fact, that's what a lot of architectures attempt to do. And there's a variety of ways you can do this. So a very sort of typical way that this might look in sort of a standard digital accelerator is that you might access your data from memory and then attempt to do a lot of computation on it once you've accessed it to amortize that accessing cost. And so for example, one way to visualize what this gives you is something called a roofline plot. This is just one way to do this. And the idea here is often this is plotted on a log-log plot so that it looks piecewise linear. On the x-axis, what we have here is this thing called compute intensity, which tells me that once I've accessed my data, how much compute can I do on it. And so if you can do a lot of compute on it, of course, you get into this compute bound regime where that accessing cost is fully or amortized. And so you're limited by your compute. Otherwise, the more compute you can do, the better your amortization is, but you're in this memory bound regime. OK, so now if you're going to build a hardware accelerator where you know very well what the memory accessing patterns are and what the reuse opportunities are, you can now really take advantage of this to try and optimize around this amortization. And so let's just come back to this kernel, which I suggested is going to be important, this matrix vector multiply. You can see here, of course, there's a lot of opportunity for reuse. You have this vector input vector element, and it's going to touch all of these sort of matrix elements. And so this is an opportunity for reuse. And in fact, the kinds of architectures that can really exploit this reuse are, for example, these spatial arrays, where we have these processing engines. We've essentially unrolled this loop spatially. And what, in fact, this allows me to do is, in fact, there's not just a reuse opportunity across this column. There's also this sort of output partial product that gets reused. And so what we do in this two-dimensional array is sort of create a structure for our hardware that's actually aligned to the data flow that we have in a 2D matrix. And so in fact, you're not just amortizing sort of this memory accessing, you're also amortizing the data flow that you might have here. So there's a lot of opportunities to take advantage of this. Such amortization is precisely what in-memory computing is going to do, and it's also going to take advantage of this two-dimensional structure. So that previous slide talked about what sort of traditional digital acceleration does. Let's see what in-memory computing does. And to describe this, I'm going to use one particular architecture for in-memory computing, just sort of as an illustration. So you can imagine here that I've got a two-dimensional array, in this case of bit cells, and it's got periphery of two kinds, one to do in-memory computing and one to do sort of standard, in this case, SRAM accessing. And the key here is that this SRAM accessing is how we're going to load this matrix element, these matrix elements into this array. What's important is we're going to do this row by row. That's traditionally the way that we do SRAM accessing. On the other hand, when I go to do this in-memory compute, now what I'm going to do is I'm going to activate all of these word lines all at once. You see, when I do this row by row accessing, I incur a communication cost on these bit lines for every access I do. On the other hand here, what I'm going to do is I'm going to apply the input vector. And in fact, I'm going to do that through a digital to analog converter in this particular architecture. So I adjust the amplitude of this signal, if you like, according to that input vector element. And what that does is it modulates, for example, the current that this bit cell provides. And so if you think about these two bit lines, bit line and bit line bar, as a differential voltage signal, then the data that's stored in here is kind of like a +1 or a -1. It takes that current and puts it either over here or over here. So essentially, this is like doing a multiplication by +1 or -1. The current on this bit line then gets accumulated. That's a multiply and an accumulate. That's essentially the computation that I'm doing in this matrix vector multiply. What's important is that now I didn't incur a communication cost for each element that I was accessing. Rather, I accessed a compute result over all these elements. And that's the amortization that in-memory computing tries to do to address this communication cost. So this is the key distinction, row by row accessing in standard memory versus accessing multiple rows, perhaps all rows in-memory computing. That's the way in-memory computing drives its gains. This can be applied to many different memory technologies. This particular architecture relates to SRAM, but in fact, our research and others are looking at emerging memory technologies, non-volatile technologies, and so on, which also scale very well and are very interesting to talk about. I'm happy to do that if anyone's interested. Okay, so this form of compute and this form of architecture actually dramatically changes the trade-offs that we now face. So let's just see how it changes those trade-offs, because this now is going to become the focus of the barriers that I need to eventually overcome, this new set of trade-offs that I have. So to do this, let's go through a thought experiment. Imagine I've got some sort of computation that needs to access a total of d bits of data, okay? And so you might do that from a memory array, which is arranged as a square root d by square root d. And I'm going to compare these two architectures, traditional one where I have memory and compute separated, and then one where I have this in-memory computing. And the metrics I'm going to look at are the ones we typically care about for memory accessing: bandwidth, latency, and energy. And then I'm going to throw this additional one in here, SNR. I'll talk about that in a moment. Okay, so what happens here is let's look at bandwidth. If I want to access all of this data in traditional SRAM accessing or memory accessing, I do it row by row. So in fact, the bandwidth that I have scales as 1 over square root d. Okay, over here, on the other hand, I access all of those rows at once. So the first order, this doesn't scale. If I look at the latency, once again, I have square root d accessing cycles in this traditional architecture, but also the length of my bit lines. The communication sort of cost scales as square root d. And so in fact, this is scaling more like d. Here, the length of my bit lines also scales as square root d. The communication distance also scales as square root d. But I'm driving that bit line for every incremental increase in that bit line capacitance with a corresponding bit cell, because I'm doing this all in parallel. And so in fact, also to first order, this doesn't scale. In terms of energy, here I have square root d access cycles, where I have square root d scaling of each bit line, and I have square root d total bit lines. So I have sort of this power 3 over 2. Over here, once again, I have square root d scaling of my bit lines. I have square root d total columns. And so here, the energy only scales as d. So it's that power d to the 1/2. That's really what I'm gaining in energy. So all of this looks good. What's bad? Well, what's bad is, of course, the SNR. So the assumption here was that the communication I'm doing is generating some amount of bitline swing set by the sensing requirements. On the other hand, over here, I'm accessing a compute result over square root d operands. And generally, that's going to increase the dynamic range requirements of my compute. Unfortunately, I need to fit that dynamic range on some bit line, which has some fixed swing. And so that squeezes my SNR. So you can see here that the SNR actually goes down as square root d. So when you start thinking about the trade-offs and the barriers, which I'm going to talk about in a moment, keep this trade-off in mind. This is the basic thing that we face here. In fact, I described in that sort of analysis this in-memory computing, sort of comparing it to standard memory accessing. But what about these architectures that sort of try to optimize that memory accessing, things like these spatial arrays? Well, in fact, if you think about it, this in-memory computing architecture is really just another spatial array, where instead of these processing engines, which can potentially distribute memory and compute, I have bit cells in a similar arrangement, which can distribute memory and compute. And in fact, it's very interesting to compare these. Let me start by just comparing the data flow. Okay, then I'll go to the compute. If we look at the data flow here, because we're dealing with these very dense bit cells, in fact, this can give me dramatic gains in reduction of the data flow that I have. In particular, on the one hand, I need to broadcast one of these operands across this array. But because I'm dealing with these very dense bit cells, that broadcast distance can be reduced. That communication distance can be reduced. This architecture also has to do such a broadcast. It does it by moving the data around. Here, that movement can be reduced. There's an opportunity to store one of the operands locally. In fact, we do that in both of these architectures. And so one of those operands is stationary and it doesn't move at all. So that's great. The other operand, in this case, is going to be, in fact, a high dimensionality number, right? This accumulation, say, across the row of a matrix. But what's interesting here is that that high dimensionality number is computed in a distributed way. This could be, for example, I don't know, an 11-bit, 16-bit, 32-bit number, whatever you think it could be, depending on the dimensionality of your matrix. But here, that number is computed in a distributed way. So in fact, we don't incur that communication cost. This is precisely that amortization that I was showing on the previous slide. On the other hand, in this case, of course, you do need to communicate this potentially high dimensional 16-bit, 24-bit, whatever the right dimensionality is, number to the edge of this array. So in terms of data flow, there's an opportunity here. In fact, it turns out in-memory computing also does some sort of an amortization of the compute. I'm going to describe this in a lot more detail. So this is that digital processing engine. I'm going to show you some real numbers that have come from both silicon measurement and also some careful post-layout simulations. In fact, it turns out in-memory computing, that architecture I showed you had these 1-bit multiplies. We can extend this to multi-bit. And I'll show you an architecture that does that. What'll be interesting is it's going to do this multi-bit compute in a bitwise way. And it turns out, in order to get the multi-bit result, before getting that multi-bit result, I'm going to do this vector inner product, multiply and accumulate. And then that amortized result over the dimensionality of the matrix or the vector is going to be used for this multi-bit compute. So I'm actually going to amortize over this dimensionality that multi-bit compute. And you'll see how that works in a moment, but these are some numbers just to keep in mind. In fact, this single bit compute can be done very efficiently. We'll actually do it in an analog way. And in fact, we can see that there's the potential here for 10x gains. OK, so these are some numbers and some potential. In fact, we've recently started to see prototypes, certainly for digital acceleration, but also for this in-memory computing acceleration. And so this is just a survey of various designs. And what this shows us is these stars are in-memory computing. Just kind of empirically, there seems to be the potential here for simultaneously a gain in throughput by 10x and a gain in energy efficiency by 10x. So it looks very good. But in fact, if I now change this axis, not to just throughput, but to some sort of metric that talks about the scale of the compute or the level of integration that I've achieved with these, in-memory computing starts to fall flat on its face. So many of these architectures move down. There's one exception here, which I'll talk more about in a moment. But this is the challenge that we have to deal with. How do we get this thing to scale up? And why has that been such a challenge? So let's talk about a few challenges that have come up. The first is that in-memory computing tends to require analog computation. And the reason for that is I've got these highly constrained, very dense bit cells. To fit compute in this constrained structure, I'm not going to want to restrict myself to a digital switch model of a transistor. I'm going to want to use the transistor for all it's worth. And that typically requires me to go analog. Okay, that's good, potentially. The problem is, with analog circuits, you have all sorts of issues, as those who design circuits know very well, related to nonlinearities and variation. So this is measurements for one of the particular architectures where we see error bars related to this sort of bitline signal or bitline discharge transfer curve. And an unfortunate issue is that, in fact, some of these non-idealities and variations get worse in general as we go to more advanced technology nodes. Of course, digital is going to keep going to these more advanced technology nodes, and for this to be competitive, it must then also be able to scale in this way to more advanced technology nodes. It's a challenge that we need to think about. Just a sidebar here before I continue talking about challenges, of which there are many. One interesting question is, can we use algorithmic techniques to sort of address some of these analog non-idealities? This is a question that was actually asked earlier, right? We're using this statistical optimization in machine learning algorithms generally. Can I not incorporate the statistics of my hardware in that training process and then just train away, or some other way calibrate out these sorts of non-idealities? And in fact, it's a very powerful and intriguing question, one that I'm very, very interested in. It's something that we've looked at a little bit. This is not using a neural network model. This is using a machine learning model called adaptive boosting, where you can actually train classifiers iteratively to, in fact, compensate for the compute errors that you had previously. Sounds very interesting. You can do this with neural networks as well, by the way, in a backward-forward propagation. You can use the forward path to compute your loss function and adapt to the hardware non-ideal. Sounds very interesting. And in fact, people have started to integrate trainers on chip to do sort of this weight tuning in response to the hardware non-idealities. One problem with this is it's chip specific, and so this might start to address that. Other research has also looked at creating chip generalized training methods. So for example, if I've got some hardware which has some variation or non-idealities, in fact, I can create a statistical model of that. And just like we do stochastic training in neural networks today, I can incorporate that stochastics in computing, in this case, my loss function. And now when I go to map a model parameters that I learned to a specific instance of hardware, so this is a sample out of this stochastic distribution of hardware, now my performance might be very good. And in fact, it does kind of work out. This is some research that we've done using MRAM-based in-memory computing. We're sort of incorporating this stochastic training where we model the hardware statistics can allow us to tolerate very high levels of variation potentially. So it sounds interesting. Here's what I'll say about this. As I want to get to higher architectures, right, integrate this into a bigger platform, a fundamental requirement is that I need to create a functional specification for my module so that the modules around me know what I'm going to do. And this algorithmic co-design, where I'm relying on something at the algorithmic level to change my behavior or change the way that I look at this hardware, poses a real challenge in creating that functional specification or that abstraction. I'm not saying it can't be done. I'm saying it's going to require a lot more research in terms of sort of working our way up this stack. OK, very interesting thing. Challenge number 2, programmability. So if we look at sort of the typical compute that's being done in these deep learning systems, this happens to be for training, but you see a similar picture for inference. You see a lot of red bars for these different kinds of workloads or classes of applications. These red bars correspond to that matrix vector multiply that I was focused on, general matrix multiplies. But actually, there's a bunch of other compute as well. If you don't address this, this is kind of like the Amdahl's law of in-memory computing. You're going to be ultimately limited by this stuff. Now, it turns out that this stuff is very different than this red stuff in the following way. Remember, this involves these high dimensionality operands, so a lot of data movement. That's why I delegated it to in-memory computing. This stuff is mostly operating on single elements. So in fact, here, traditional digital acceleration can really shine. But the point is, whatever architecture you're going to build is going to be a heterogeneous architecture involving in-memory computing integrated with this other kind of digital acceleration. And once again, this is where that hardware specification for that module so that it can be integrated in this larger architecture really becomes critical. OK, moving up from the architecture level to the software mapping level, of course, whatever architecture I create, I want to map a bunch of different applications onto. And so now I've got a virtualization problem, OK, where I, for example, need to reconfigure my in-memory computing. I need to load new matrix weights in. I need to configure bit precisions, all of these kinds of things. And remember, the way that I've described it so far, in-memory computing really only solves or addresses that matrix vector multiply problem. None of this virtualization overhead. Okay? Now, you can analyze this virtualization overhead where, for example, you need to load new weights or you need to load new input activations, and that can sort of degrade some of your gains. You can analyze this using similar sorts of reuse arguments to see how this plays out. But this needs to be done for the design points that in-memory computing is operating at. In fact, this is an area that our research is keenly focused right now. One interesting insight that I'll give you, and I don't have answers here yet because, like I said, this is ongoing research. But one very interesting insight here is the fact that in-memory computing has this density advantage by exploiting these bit cells. Turns out that these virtualization overheads are often kind of communication overheads. You're loading new configuration bits or new weights. In fact, by reducing the size, increasing the density, you can do a lot to actually get gains in this virtualization overhead. But we need new algorithms. We need algorithms that take advantage of that opportunity. Okay, so these are some challenges. What are the potential paths forward? I hope there are many, and I hope that we'll all sort of work on them in various ways and come up with the best ideas eventually, because I do think there's some potential here. What I'll do is I'll talk a little bit about one of the paths forward that we've been exploring in my lab. And that has been to address this SNR trade-off that I said was fundamental to in-memory computing. We're going to try to do analog compute, where the noise is really limited by the variations and non-idealities of analog compute, but we're going to try to do it in a way that's very precise, that's a little bit more robust. And so for that, we move to the charge domain. The idea here is the following. A bit cell is going to look like this. I'm going to store a 1-bit weight in my bit cell. I'm going to apply a 1-bit activation along some sort of a word line. And then I'm going to do some sort of a multiplication in that bit cell, which is going to give me a 1-bit output. And I'm going to store that as charge on a capacitor. Now, this 1-bit output, because it's a binary output, is perfectly linear. You can perfectly fit a line to these 2 points. Okay? But what I'm now going to do is I've stored this as charge, an analog quantity, although it's binary here, on this capacitor. Now to do the accumulation, so this is multiplied. To do the accumulation, I'm going to short these capacitors together, and that's going to give me my accumulation. So the accumulation, which remember is what actually gives me the amortization that I'm going for, is done in this charge domain. And the value of this is the following. How precisely I can do this depends on a capacitor, not a bit cell current. Bit cell currents are messy things. They depend on semiconductor parameters like mobilities, device parameters like threshold voltage variations. Capacitors depend on geometric properties. These are much, if I was to bet on something, I'd bet on those. In particular, as technology scales, this is something that can hold up, potentially, needs to be proved. In fact, it turns out that this capacitor is actually implemented in the metal stack. So it's implemented in the metal fingers that are the metal wires that I would normally use to connect up my circuits. So this can be implemented on top of the bit cell with no extra area overhead. There is some overhead of 2 additional transistors to do this multiply in this 1-bit cell. But it turns out, I guess I didn't show that, it turns out that that overhead can be small. I'm happy to talk more about that in this 65 nanometer prototype, but also in more advanced technologies that we're looking at. Okay, so we've actually built a chip that does this. This is where I think we've been able to achieve sort of the state-of-the-art scale in-memory computing. So this is a 2.4 megabit, 64-tile in-memory computing array. Here it is over here. What I'm showing here is the transfer function for the 512 neurons that I have. So I have 512 columns in this memory array. I'm showing the transfer function. The error bars there, that's the standard deviation across those columns. And so you can see that they're very tight. So indeed, this capacitance-based compute does give us the sorts of stability that we need, which we can now use to create a robust functional specification for this module, so I can move up to the architecture level. These are just some numbers. I think you'll have the slides available, so you can look at these if you like. We've done, this is an old slide. I just copied it, in fact, from a previous presentation. We've mapped state-of-the-art neural networks to this thing. So sort of like 20-layer, 25-layer neural networks is a common thing that we've done here. And indeed, we achieved the performance that you would expect based on a software model, because this analog compute is robust. So now the next step is, of course, you want to move this thing into a programmable architecture, into a bigger architecture. And so that's what we've done here. So this is an architecture that incorporates in-memory computing. It's a little bit smaller than the previous chip that I showed. That's only because of die constraints. This incorporates this thing, in-memory computing, with sort of standard SRAM, CPU. This is a RISC-V CPU. Some hardware for doing memory management, a DMA, a direct memory access module, scheduling hardware, timers, and so on. What I want to talk about is this in-memory computing unit, which basically takes that charge domain computing array from before, but it does the following. It incorporates interfaces around this thing so that this sort of massively parallel bitwise operation that's done inside this accelerator can be unified with the rest of this processor architecture, which is a 32-bit microprocessor. So we need these interfaces that go from these 32-bit words to this massively parallel bitwise operation, which now allows this thing to exist in the standard processor memory space. This is going to be useful for programming this thing. The other thing that we've done is we've introduced this near memory data path. So hanging off of each of these columns is an ADC. It turns out it's an 8-bit ADC. We've introduced this near memory data path. Remember all that other compute you have to do surrounding matrix vector multiply? All of that is done in this digital accelerator in the digital domain close by. Another thing that we've done is we've extended this from single bit operations to multi-bit operations, up to 8 bits. But we do it in a bit of a weird way. So here's what's happening here. This memory array stores in each of its bit cells only a 1-bit number. And the word lines are driven, once again, by a 1-bit number. So to extend this to multi-bit compute, what we're actually going to do is store the multiple bits of my matrix elements in parallel columns. This is what we call bit parallel operation. And we're going to apply the input activations or the input vector elements in a serial operation, one at a time. Now, what ends up happening here then is an inner product operation of a binary vector. Now, in the digital domain, what I can do is properly bit shift this to apply the appropriate bit weighting, and then accumulate these guys up in the digital domain so that I can extend to multi-bit compute. In fact, any bit precision you might want. The problem is the actual signal to quantization noise ratio that you get with this, the kinds of quantization that it does, is a little weird. Here's the issue. This is a very long column. I want it to be. That's how I amortize the communication costs and, in this case, all the overheads of this conversion in in-memory computing. But when I do that, if you think about it, the dynamic range I can have on this analog signal corresponds to each of these binary operations that I'm doing here. If I have, in this case, 1023 rows, or sorry, 2304 rows, I have a very high dynamic range going into my ADC. I don't want to build a 12-bit ADC or whatever I need here, because that can be very energy intensive. So I restrict myself to an 8-bit ADC. So there's some loss of dynamic range across this. And so in fact, the signal to quantization noise you get depends not only on the bit precision of your input vector, depends not only on the bit precision of your matrix element, it also depends on the dimensionality that you're doing this compute. If you restrict yourself to 255 dimensions, 255 dimensionality, this perfectly emulates integer compute, but not for any other higher dimensionality, because I can't preserve that full dynamic range through this ADC. But that's actually OK for 2 reasons. First of all, in the bit precisions we might be interested in, sort of 2 to 6 bits, 2 to 8 bits, in fact, the signal quantization noise ratio is about close to what you get with integer compute. But the second thing is, this quantization is a very robust quantization. It's something I could build a model for and incorporate into my training processes like I do for quantized neural networks anyways, and use the model parameters I get on all my chips because it's stable. So what we've done is we built the development board for this thing. This is the one here. We've also built the software libraries for this thing. Let me tell you a little bit about how far we've gotten. So we have software libraries that in fact integrate in Keras or TensorFlow. And they looked as follows. So you can declare sort of or instantiate various kinds of layers. These could be dense, fully connected layers or convolutional layers, what have you. And then what you would do is replace those, if you like, with sort of classes, superclasses of these layers that we've defined. And these let you do 2 things. These let you define the input quantization level, and they also let you define what kind of quantization this is going to do. We have 2 kinds of quantization. Well, we have 2 kinds of quantization, which we set by a flag called chip quant. If chip quant is set to false, this reverts to standard integer quantization. If chip quant is set to true, this does that weird bit serial, bit parallel quantization that I showed on the previous slide. Now, it would be nice if you can go from here directly to the low-level code that can then be mapped to our hardware, where we've sort of incorporated all those virtualization algorithms. So what we'd like to do is actually build an auto tuner or auto code generator. We haven't gotten there yet. And so what we do have is the low-level libraries that you can sort of manually map to. And so these are low-level libraries in Python. And then there's also some in embedded C, which actually delegate the compute to the chip. What we really want to do is move automatically via a compiler or via auto generator from here to here. But to do that, we need to really understand all of those virtualization trade-offs and build up those algorithms, which is something that I mentioned we're trying to do. Okay, so we have this chip. It's implemented in 65 nanometer CMOS. We've measured it. It gives us very stable compute. In fact, the SQ&R you get looks very much like the bit true sort of expected SQ&R. That's in the dotted lines, and then these markers are the actual chip measurements. These are just sort of time domain waveforms of outputs coming from here, so you get very precise compute. We've used those software libraries to develop a bunch of different neural networks. These happen to be 2 demonstrations of a CFAR10 network at 4-bit quantization for activations and weights, and also for 1-bit quantization, and you can see the kinds of energy numbers that we can start to get here. Okay, those are the conclusions. Let me just leave those up. I know we're running a little bit behind in time, so let me leave those up in favor of any questions if there are any.
Do you do negative weights?
The question was, can we handle negative weights? And the answer is yes, we can handle negative weights. It just requires us to do the proper compute down there in the digital domain. So we can do standard 2's complement, for example, representation for our matrix elements and our input vector elements. Yeah. Yeah. So remember, each column, I'm doing operations in a bitwise way. So I know what my, for example, most significant bit is. It might correspond to some sort of assigned bit, or in 2's complement, some sort of representation of assigned bit. And so once I've done that 1-bit compute on the MSB, I can treat it as a negative number or a positive number in the digital domain when I add it to my other compute in order to do proper 2's complement multiplication and accumulation.
Question here. When you were describing this SNR trade-off and in terms of using multiple bit lines, I wonder when you do the comparison on energy efficiency, a fair comparison would be actually in the conventional implementation, maybe the supply voltage could be lowered and essentially they achieve also lower SNR, but it comes at the benefit of energy efficiency. So
great question.
The comparison then would be a bit
So
fairer.
let me tell you what we have done. I'm very uncomfortable with just scaling the supply voltage because now I wonder if the variations are getting to you to the point where I no longer have a robust specification of my quantization. But here's what we have done. So what you can do is you can do your accumulation. Essentially that ADC is converting the accumulated result. What you can do is do your accumulation. Maybe the requirement for the full dynamic range here was a 32-bit accumulator. What you can do is instead do an 8-bit accumulator or a 6-bit accumulator. I would argue that that is a more fair comparison. We have done that comparison, and indeed, this gives us the same sorts of energy gains that you'll get. That accumulator, in fact, is sort of marginal in determining the total energy. But I'm happy to share those numbers with you if you're interested. That also requires, by the way, some kind of stochastic rounding when you do that accumulation. And that also has some overheads associated with it. You can't just lop it off and do an 8-bit accumulate.
So you talk how you map matrix multiplication to the device. How exactly do you do convolutions?
How do we do convolutions in the device? So in fact, if you think about it, what you're doing actually for each sort of matrix vector multiply is you're just doing a vector and a multiply. In convolution, what you'll do is you'll shift the elements of that vector. And so in fact, it's in the periphery of this array that we shift the elements of that input vector, which is precisely how we drive those over the word lines of the array. And there's some interesting questions about how you can take advantage of convolutional reuse in the communication of that input vector, large dimensional input vector. Happy to talk more about that if you're interested.
Yeah, I find it very interesting discussions like how flexible the data flows you can map on there are. Can you comment a bit on your efficiency? Is it very different because the type of kernels, convolutional fully connected, the size of the kernels, or does it work across the whole board, or is there a sweet spot?
Great question. So indeed, we do want to be able to support many different kinds of neural network models, and that's something that we, in this programmable architecture, can do, and in fact are working on architectures that can do that even more sort of aggressively. There are concerns. So the question you're asking is, what kind of, perhaps ultimately the question here is, what kind of utilization do you get across different kernels. What is the most efficient? So, I mean, I think part of it is, you can break your energy costs down into moving the data flow, so moving the input activations across, and then you can come back to that reuse argument. And then the other question here is, for these different kinds of neural networks, you have highly varying sizes. And I have, some amount of hardware, and of course I'm going to virtualize that eventually. But for now, there's some amount of hardware, and there is some utilization loss. So we've tried this across a bunch of different neural network applications. I'm happy to describe the details of the corner cases here, but as long as you can put all of your weight parameters on chip, and by the way, as you're moving to 4-bit precision, this is something that's actually pretty viable to do. You start to think about the size of networks that you have. In fact, if you can do that, you can get very close to full utilization on this. We need to tech this for more different kinds of networks to be able to make sure that this is playing out and what kinds of considerations you get. But the question you're really asking here is really one, how do you virtualize for these different kinds of data flows you have in different neural network models? And that's where we're really focusing these days on the algorithms for mapping.
All right, we're coming into the break now, so if you have any more questions, please find Naveen during the break. Let's thank all the speakers again. That was a great session.